Great. So this is visible to everybody, right? Okay. So yesterday we had talked about introduction to queuing theory, and today we are going to dig deeper into it. All right. So we had talked about that in computer networks. How would it look like if we are having, a system where so many packets are actually entering into that system, they're using the resources of that system and forming a queue. So here too, it is an example that has been given here, that is, suppose source A and source B are sending a lot of packets to a particular router, and the packets are coming into a very higher quite a higher rate as compared to the rate of this line card, that is R. Okay, so in that case, what would happen? The packets would get queued at the router. All right. So in this case, if we are using queuing analysis, so we will be able to find out that what is the average time that a packet would have to wait at the router. How many packets on an average will wait at the router? Okay, and that means the router's buffer or queue. Okay, so for finding out these kind of analysis, or for doing such kind of analysis, we can use queuing theory. Okay, so we have seen this example yesterday also, that we would have a particular customer population from which customers are actually entering into the system, forming a queue, and then they are going to different servers to get served with whatever request that they are having. Now, how much time will they spend in the server will depend upon, that is, what is the size of the job that they have come with to the server. This is assuming that the servers are identical to each other. If you remember yesterday's properties that we were doing, that we consider a system with multiple servers given that the servers are actually identical to each other. That means the service that they are giving, that is identical to each one of them, all of these servers that are present in the system. If the service rate that they are giving is different, then in that case we will form separate queues for these different servers. Okay, so if we are considering the same system with multiple servers, the servers are supposed to be identical. This is what we assume when we are doing queuing analysis. All right. Now, this Kendall notation we have already studied, so I will not get into the Kendall notation again, but I will again just tell you, this is the inter-arrival time distribution. This shows, if you are seeing the hand in the slide, if you're not seeing the hand in the slide, let me know. Okay. So A represents the inter-arrival time distribution, S represents the service time distribution, M is the number of servers, B is the system capacity, K is population size, and SD is the service discipline. So I had also mentioned yesterday that system capacity is in general considered to be infinite. Okay, if it is specified properly, that means it is specified that what is the size of the system. Okay, then in that case it is not finite. Otherwise, if it is not specified, then it is considered as infinite. Similarly, for population size, it is in general considered to be infinite, otherwise it is specified. Okay, and as for the service discipline, in general it is considered to be FCFS, otherwise it is specified that what is the scheduling discipline. So if it is not specified to you, that means it is FCFS. Otherwise it will be specified to you that what is the service discipline that is being used here. Okay, so we had started with Little's theorem. So let me just tell you that how will it look like. Okay. All right. So let me get to this one. So what we were talking about Kendall notation, no? So Kendall notation. So we had all these, service time distributions, arrival. So first is arrival time distribution, then service time distribution, then what is the number of servers, then you have the system capacity, then you have the population size, and then finally you have the scheduling discipline. I am just putting it as SD. Okay. So now in general, so these will be the distributions that are already given to you. This is the number of servers. This is the system capacity. It is in general given out as infinite. If not, then it will be specified. Okay. This is in general considered to be as infinite. If not, then it will be specified. This is in general considered to be as FCFS. If not, then it will be specified to you. So suppose I am considering that A is following exponential distribution. So it has memoryless property. S is also following exponential distribution. So that is also following memoryless property, and you have only one server. Okay. So how do we represent the Kendall notation? It should be written as m/m/1 slash population size is infinite, K is infinite, and SD is FCFS. So ideally it should be written like this. Okay, but writing every time this much big is too much, right? And anyways, these are your default scenarios that you are considering. So in general, if these are default, by default, infinite, infinite, and FCFS, we simply write it as like this, MM1. Okay, so this represents a queue, okay, in which the arrivals, the inter-arrival times follow exponential distribution. The service time distribution also follows exponential distribution. There is only one server, and of course you have infinite buffer capacity or infinite system capacity, infinite population size, and FCFS scheduling discipline. Okay, so this is the representation. So we can have like n servers, because we can have any number of servers that we want to have. Okay, now there were other distributions also that we were talking about, that is general and deterministic, very default distributions. Okay, so three mostly used distributions are these, exponential, then general, then deterministic. That's what I had told in the last class. So you can have several variations in this one. You can have MG1, MGM, or GG1, or MD1, and so on and so forth, So there can be so many variations on this, depending upon, what is the arrival or service distribution that you are having, and what is the number of servers that you are having. Okay, so this is how your system is working. I hope that this part is clear. If not, you can ask me questions on this, and I will now start looking into Little's theorem. Okay, so I would suggest you guys to better note this part down. I know that although you will have the recordings of this lecture, but I think if you do it by your own, it will help you out further. Okay, so what was the Little's theorem? Let me just get again into this. What was the Little's theorem? We had done that, no? Little's theorem. So does anybody remember what was the Little's theorem I had taught in the last class? Nobody remembers? This is weird if nobody remembers that. What is the Little's theorem? So what was it? That the expected number of, or average number of jobs in the system, number of jobs in the system is equal to what? Arrival rate times what is the time on an average that is spent by the jobs in the system, right? So time spent in the system. We have to prove it. Okay. So this is the Little's theorem. You can also consider it as, average number of jobs in the queue is equal to arrival rate times average number of times spent in the queue. Average amount of time spent in the queue. Sorry. Okay. So this is the Little's theorem. And now let's get to this part. All right. So what we are going to do? We are going to observe a system. Okay. So what are we going to observe in this system? We are going to observe a sample history of the system from time t equals to 0 to indefinite future. Okay, so for infinite time, you are going to look into this system from starting from time t equals to 0. Okay. And you will be recording values. Okay, you just consider that what's happening in the system is that there is some arrival that is happening, and then those are going out of the system, departing from the system. You don't know what's happening inside. Okay, so you are simply one observer who is observing who are entering and who are departing out of the system. Okay, basically how many arrivals are happening and how many departures are happening at what event of time. So you will be recording those values. Okay, so now suppose you do this for infinite amount of time, and you are denoting certain values here. So first thing is NT. Okay, NT is what? Number of customers in the system at time t. Alpha t is what? Is the number of customers who arrived in the system between times 0 to t. Okay. So n of t is number of customers that are there in the system at time t, and alpha t denotes customers that have arrived in the system in 0 to t time. Okay. Ti is the time spent by the ith customer in the system, and what can we find out from this? So the time average of customers in the system up to time t, how will we find that out? Okay, we can find that out by doing this integration from 0 to t n tau d tau, right? So nt is equal to 1 upon t integration 0 to t n tau d tau. It is going to give you the time average number of customers in the system up to time t. Okay, now we are going to take some assumptions. Okay, so what is the assumption here? That is NT converges to a steady state n as t tends to infinity. Okay, this assumption holds in many systems. So what we are going to do today, so how we are representing this statement, that is NT converges to a steady state as a steady state n as t tends to infinity, we can write it as n equals to limit t tends to infinity nt. Pretty simple here. Now we can find further averages. We know that alpha t is the amount of customers or amount of arrivals that are there between times 0 to t. Okay, so the time average of the arrival rate up to time t can be given by alpha t by t, and we denote it as lambda t. Okay, so here again we take the same assumption which holds for many systems, that is lambda t converges to some lambda when t tends to infinity, that is limit t tends to infinity, lambda t is equal to lambda. Okay, so then the average time spent in the system per customer up to time t, that also we have denoted earlier. So if you remember, this is the one we are talking about right now. Ti is the time spent by the ith customer in the system. So how can we represent the average time spent in the system per customer? So that will be given by TT is equal to summation I equals 1 to alpha T, because alpha T number of customers have arrived into the system between 0 to T, up to time T basically. So summation I equals 1 to alpha T Ti by alpha T. That will give you the average time spent in the system per customer. So now what is the assumption here? So assumption is that Tt converges to some T, and limit T tends to infinity, Tt is equal to T. Okay. So now what Little's theorem says that n is equal to lambda T. Okay. So we have to prove that, okay, we have to give some kind of a proof that, you know, that whether it actually happens or not, that is n is equal to lambda T. Okay, I hope that this one is clear to you. N equals to lambda T. It has fallen upon this graphical parts anyways. So we are going to give a graphical proof of Little's theorem. Acha, before I go any further, I forgot to mention it to you at the starting of the class that whatever I am teaching today, entire slide and everything, you will get it from Bertsekas and Gallagher's book, okay, on data networks. I have already mentioned the book in the reference section in the first slide that I gave to you for the first module. So please follow that book. That book is widely available in our library. It is also available online, I suppose. So please go through the book for, you know, any further details for understanding of the proofs, etc. So, okay, let me just get back to this. Now let's get to the graphical proof. So what are we talking about here? We are looking at the system. Okay. So this is the time for which we are looking at the system. This is representing the time axis here. And now number of arrivals is denoted by alpha T, and number of departures, alpha tau here, and number of departures is represented as beta tau. Okay, you are looking from 0 to tau here. This is at up to T you are looking. Okay, so now up to T we are looking at the system. Okay, so what's happening, you as an observer, when you are observing into the system, what you will see that, okay, there was an arrival and then there was a departure. These points, so suppose T1 is here, no, this represents that there was an arrival at time T1. Okay, there was another arrival at time T2, but as an observer you're also seeing the departures. Okay, so there was a departure at this particular point of time, there was a departure here also, there was a departure here also. Okay, so this is basically following a staircase graph, because nothing else you can see. It's a black box, you see just the arrivals and just the departures. And you know, there is no multiple arrivals happening in the system. One arrival, departure, one arrival, departure, like that it's happening. Okay, so that is why it will look like a staircase graph, like how it is showing. Okay, so alpha tau represents the arrivals, beta tau represents the departures here. So at time T1 there was a arrival, so that is why here you have a bar here. Again, you know, at T2 there was a departure, so this is a bar here. So like that, the stair is going up and up, and you are looking at the system at time T. So suppose up just before time T there was an arrival here. Okay, so this was the arrival here, and then you just stopped at time T and you want to see that, you know, you just want to look at the system at time T, that what has happened until now. Okay, so this is the stoppage point here. All right, so there has been no departure after this arrival into the system. So what is this representing? So that means customer 1 enters into the system at time T1. Okay, and then leaves the system at this point of time. Okay, so the amount of time that the customer actually spends in the system is this much. Okay, so that is T1. Ti was representing the amount of time that a job or a job or a customer spends in the system. We had the representation given just in the previous slide. So for customer 1, the amount of time that the customer 1 spends in the system is given by this, because arrival is here and then there's the departure. Similarly, for customer 2, you have an arrival here, then there is the departure. So this is the time that the customer 2 spends in the system. Okay, and if you see this entire stuff, okay, this entire if you just find out the area of this graph and all, then you will find out that what is the number of customers that are currently in the system. Okay, so now, so I hope that the graph is clear to you, how the graph looks like. Now we will get into further portions. So the system is initially empty. Okay, that means n0 is equal to 0. We represent alpha t as number of arrivals, beta t as number of departures, and alpha t minus beta t will be the number of jobs that are in the system. So that is equal to nt. Okay, so the area of the shaded part, okay, that's what I was saying. This is the green shaded part, the area of the shaded part, including this one. Okay, because there was also an arrival here. Okay, so this entire area of the shaded part is going to give you that what is the number of jobs that is there in the system between time 0 to t. Okay, so that you can find out using the integration from 0 to t n tau d tau. So how do we find this out? Okay, how do we find this n tau value, and how do we find that how much of average number of customers actually in the system are there? Okay, so look at this graph. Okay, there was an arrival here, then there was a departure here. Again, there was an arrival here, then there was a departure here. They are following a staircase graph. If you just connect these points, okay, you will actually see it as a rectangle, right? As you can see the red block here, you can actually see this block as a rectangle, and this portion anyways talks to you about, this width. This actually talks to you about that what is the time that the customer actually spent in the system. All right, so the area of this first block, this is the time that the first customer spent in the system. Okay, so the first block, that area is t1. Area of the second block, if you try to find, if you connect this one and you find out what is the area of the second block, that will be t2, and therefore so on and so forth, it will go on. Okay, and we know that how many arrivals are there in the system? There are alpha t arrivals. Okay, so if we connect, there should be alpha t such blocks. Now we will find alpha t such blocks, but there was an issue there, right? That there was an arrival here and there was no departure. Okay, but for the time being, what we can do is we can simply consider this as an entire block. Okay, we consider this as an entire block, and then we find out the area of this total region. Okay, how do you find the area of this total region? Simple, summation I equals 1 to alpha t ti. Okay, so this is the full up to this portion. You know that what is the area of this graph. Now we have found out up to this part, this portion. Okay, now let's find out up to this much, how much of area was there. Okay, so this is, you can represent it in terms of, up to this much only departure has happened. Okay, so similarly with the help of departures, you can actually find out the area of this region. Okay, so that is summation of I equals 1 to beta t ti. This is the area of this shaded region. All right. So Of course, this area, that is this area, will be smaller than this one. Yes. So if we represent it, if we compare these areas, what it will be look like? Summation of I equals 1 to beta t ti less than equals to the total area that we are actually looking for, that is 0 to t and tau d tau, less equals to summation of I equals 1 to alpha t ti. Okay, so this is comparing the areas, we get this. Now, can we represent it in a better way? So what we do is we divide this equation by t and then adjust it. Okay, so what we do, we find out, we just do it something like this. If you just divide it by t, that is summation of I equals 1 to beta t ti by t. Okay, so in that what we are doing is, we know that beta t by tau would be what? Average number of departures that are happening from the system, right? So we just multiply the numerator and denominator with beta t here. So sorry. So beta t by t times summation I equals 1 to beta t ti by beta tau. This also represents some term, remember, less than equals to 1 by tau summation 0 to t and tau. This also represents something from the previous slides, you will remember. Then less equals to, again you divide this by t and multiply the numerator and denominator by alpha t. Okay, so you get these terms. Okay, now when t tends to infinity, okay, remember the slides that we were talking about, the second slide. Okay, so when t tends to infinity, then alpha t by t and beta t by t will converge to lambda. Okay, so and summation I equals 1 to beta t ti by beta t and summation I equals 1 to alpha t ti by alpha t, these will converge to t. Excuse me. So what can we write here? Now we can write that n is equal to lambda t. Okay, so this gives you your Little's law, that is the average number of customers in the system is equal to the arrival rate times the average amount of time spent by the customer in the system. Okay, so this is n is equal to lambda t. Now similarly, like this, you can also find out that nq is equal to lambda w, where nq is the average number of customers waiting in the queue and w is the average waiting time in the queue. Okay, so this proves your little law. It is a graphical representation actually. Okay, it is a graphical proof. So please go through the book once again and you will, there's much more that is written in the book. Okay, it's very nicely given there. This is a smaller version of it. So please go ahead and check that out. And let me go ahead a little further. So we have until now done only the graphical representation of Little's theorem. Graphical proof of Little's theorem. But what is the probabilistic form? Okay, so let us get to the probabilistic form of Little's theorem. Okay, so in Little's theorem, NTs are experimental observations which are also called sample path or trajectory. Okay, so we can say that, right? We have already seen that NTs are observations that we are looking for. So they can also be called as sample path or trajectory. Now, statistically, we can say that NT is a discrete random variable for each t, right? So we can formulate the Little's theorem like this, okay, by considering averages. So how can we write it? That is NT bar is equal to summation of n equals 0 to infinity n pnt. Okay, what is pnt? Pnt is that probability that n of t is equal to n. Okay, that means n experimental observations you have taken until time t. Right. So this is the representation of nt bar. Now let's get to the further points. So at steady state, of course, we know that it happens in most systems, that at steady state, P and T will converge to Pn. Okay, so that means as T tends to infinity, P and T converges to Pn. So what will be the average number of customers at steady state then? So at steady state, we can write that n bar is equal to summation of n equals 0 to infinity npn. Okay. So why? Because n bar t converges to n bar as t tends to infinity. Okay, so that is why we are writing n bar is equal to summation n equals to 0 to infinity npn. Similarly, tk bar will also converge to t bar. Okay. So now comes the property which we call as ergodicity. Okay. So what do we mean by ergodicity? Any MNC student is there? MNC? Anybody from mathematics and computing? Have you heard of this term ergodicity? There are students from mathematics and computing, isn't it? You need to say yes or no. There are students from MNC, right? I think who gave the answer for the memoryless property? You are from MNC, right?
I'm from PhD, ma'am.
You're from PhD.
Yes, ma'am.
Okay, okay. Anybody, is there anybody in this class from MNC or we do not have? I don't know. I have to check in that case. Anyways, anybody knows about ergodicity? What is ergodicity? Okay. Okay. So I'll just give you a very simple definition of ergodicity. Okay. So it simply means that the time average through any sample path of an experiment is equal to the ensemble average. Okay. So then we say that it follows the ergodicity property. Okay. Again, I will say that the time average through any sample path of an experiment is equal to the ensemble average. And then we say that it follows the property of ergodicity. Okay. Or let me put it in this way, that the experimental time average of any process converge of a process, basically the experimental, if a process follows the property of ergodicity, then the experimental time average of the process converges to the theoretical mean of the steady state distribution with probability 1. Again, the experimental time average of a process converges to the theoretical mean of the steady state distribution with probability 1. Okay. So this and all these are, basic probability distribution. Okay. So I'm just giving you the definition here. I hope that you have written it down. Okay. Otherwise, it will be difficult later on. All right. So all right, so I hope that this one is clear to all of you. Now with that property, by the property of ergodicity, n becomes equal to n bar and t becomes equal to t bar with probability 1. Why? Because again, experimental time average of a process converges to the theoretical mean of the steady state distribution with probability 1. What is the theoretical mean that we are getting here? That is n bar. N bar equals to summation n equals to 0 infinity npn. Right? So with ergodicity property, n becomes equals to n bar and t becomes equals to t bar with probability 1. So now what we can consider? We consider that let lambda is equal to t tends to infinity. So expected number of arrivals in time in the timestamp 0 to t divided by t. We can write lambda like this. Okay. So now then we can represent the Little's theorem in a probabilistic form as this. That is n bar is equal to lambda t bar. Okay. So I hope that you are all clear about these things. All right. Now let's get to MM1 queuing system. So we have already known about Little's theorem. Okay, so now we will see different proofs of the MM1 queuing system. Okay, how do we find out the different values of an MM1 queuing system? Okay, so this is how an MM1 queue looks like. We have a queue. Okay, we have a server. Lambda is the arrival rate. Mu represents the service rate of the server. And once a job is served, then the job is the job departs from the system basically. So now what do we know from Kendall notation? If it is given as MM1Q, that means what? The arrival time distribution follows exponential distribution. The service time distribution follows exponential distribution, and you have one server. The system capacity is infinite. The what else? System capacity is infinite, and then the population size is infinite, and the scheduling that is happening from the queue to the server is following FCFS. Okay, so this is what we know of this system. A lot of things are given to you. So anyways, it is given here that the customers arrive according to a Poisson process with rate lambda. Okay, so this is what is given to you. Now I had asked you a question today, no? So please go ahead and check that question about exponential and Poisson distributions. Okay, so now I will get into this proof anyways. So customers arrive according to a Poisson process with rate lambda. The probability distribution of the service time is exponential with mean 1 upon mu. Mu is the rate of service. Okay, we have only one server. There is no buffer or population size limitations, as I mentioned earlier, and the service discipline is FCFS. So this is all the information that is given to you. Now, we have mentioned that the arrival process is a Poisson process. Okay, so what are the properties that it will follow? Okay, so it will be a stochastic process, right? What is a stochastic process? Does anybody know? How do we define a stochastic process? I told all of you to study, no, Rajjan's book for all of this. Why didn't you guys study at all? I'll just tell once. Okay, what is a stochastic process? So basically, stochastic process is a collection of random variables. Okay, it's a collection of random variables over discrete or continuous times. Okay, how do we represent a stochastic process? Let me just show you. These are very important things. If you do not know these parts, or if you do not just pay attention to these parts, there's no point in doing queuing theory at all. Okay, so if I have to mention what is a stochastic process. So what I was telling, it is a collection of random variables over discrete or continuous times. Okay, how do we represent it? Xt is a random variable. T can be equals to 0, 1, 2, and so on. Okay, or you can also write it as xt t greater equals to 0. All right, so this is your stochastic process. All right, now what I was talking about, I was talking about Poisson process. Okay, where was it? All right, so Poisson process is a stochastic process that is AT such that t greater equals to 0, taking non-negative integer values. Okay, then we call it that it is a Poisson process with rate lambda if it follows these three conditions. Okay, any stochastic process taking non-negative integer values is known to be a Poisson process with rate lambda if it has the properties that is AT represents the total number of arrivals till time t. The number of arrivals occurring in disjoint time intervals are independent, and the number of arrivals in any interval of length tau is Poisson distributed with parameter lambda tau. That is, for all t tau greater than 0, this must follow. That is, P of at plus tau minus at is equal to n is equal to lambda tau power n by n factorial times e power minus lambda tau for n equals to 0, 1, 2 and so on. Okay, so I'm sure you all know about this. Okay, the property of from the Poisson distribution property that I had asked you to study about. You all know about this property, and these are the two properties, of course, that are there. Okay, so this we call any stochastic process to be a Poisson process if it follows these three properties. All right, so I am out of time for today's class, so I'll stop the class here itself, and next class I will go ahead and continue with MM1Q and its properties. So any questions for today's class, from today's class?